Okay, today we're going to talk about the Chatlier principle, and this is a fun one. So, what is the Chatlier principle? I've defined it here for you. Basically, if an external stress is applied to a system in equilibrium, the system adjusts to offset the stress. That's kind of like what we do, right? If we have our normal life, and if something happens that adds stress to us, like taking chemistry class, what do? You adjust to offset the stress and go back to normal, right? So if this is what we do when we are challenged in life. That's exactly the same thing that a reaction in equilibrium would do. If a stress is added, it would have to adjust to go back to what it was. Now, the best way to teach you the Chatlier principle is doing practice problem. So I'm going to quickly go over what are the stress that can be added, and I want to put up a practice problem and I'm going to do it, and I want to teach you why we're doing a practice problem. So you can add or remove a reagent, and that's the external stress, and the system has to adjust to offset that. For example, if I add a reagent, it would have to shift to consume it. If I remove a reagent, it would have to shift to make more of it. Change in volume and pressure. If you change the volume and pressure, you're changing the system, you're adding a stress, you would have to again adjust to offset that. Now, one thing that I want you to remember about pressure and volume is that, do you remember ideal gas law? Yes, you do. If you remember that, there was also Boyle's law, which was P1V1 equals P2V2. So what I want you to remember from that is that pressure and volume were on the same side, so the relationship is inversely proportional, right? If the pressure goes up, the volume has to go down, right? So they're the opposite. Or if the pressure goes down, the volume has to go up, okay? Now, and then changing the temperature. If you change the temperature, then you are also adding a stress, and it will have to adjust to offset the stress. So far, so good. So these are the possibility. Now, what we're gonna do, we're gonna do a practice problem to kind of show you what I mean by that. Okay, so let's do this. So here is my practice problem. I'm gonna put up a reaction, and then I'm gonna ask you a bunch of questions. I want to add different stress to the system, and we're going to go over what would happen. So here is my reaction. I have carbon dioxide gas plus H2O water. It's an equilibrium reaction. Goes to carbon dioxide gas and H2 gas, okay? And then the delta H of this reaction is negative 201 kilojoules. And you'll see why that matters in a second, okay? Now, here is the stuff that we want to go over. Number one, what happens if you add CO2? Number two, what happens if you remove carbon monoxide? Okay, you guys are good so far. Okay. Now, the next one is what happens if I increase the volume? Next one is what happens if I increase the pressure? And next one is what happens if I increase the temperature? And then the last one is what happens if I remove H2O? Let's add one more. What happens if I add a catalyst? Okay, so these are the stress that could happen. We're going to go over what would happen when, what's going to happen if any of these stress are added to the system. You guys ready? And one thing that this is carbon monoxide. So you erase that. Okay, Are you ready? Let's do this. I'm going to show you Le Chatlier principle using this example. So the first one is, what happens if you add carbon dioxide? Okay, where is carbon dioxide? Carbon dioxide is right here. So what happens if you add carbon dioxide? Now, if you add carbon dioxide, that means now you have too much carbon dioxide. It would have to shift to the left, to the reactant, to use up that carbon dioxide. That makes sense? I'm going to repeat it again. So the first one is, what happens if you add carbon dioxide? If you add carbon dioxide, what's going to happen is it would have to shift to the left, because if I add this, now I have too much product. Now I have too much of this, it would have to shift to the left, so I would consume the carbon dioxide and I'd go back to my equilibrium equation, concentration. Yeah? Okay. So if you add carbon dioxide, it would shift to reactant. Shift to reactant. Okay. Now, what do you think would happen if I remove carbon monoxide? If I remove carbon monoxide. So carbon monoxide is right here. If I remove it, so if I take it out of this equation, right? If I remove this, then what do you think is going to happen? The system has to shift to the left to make more of carbon monoxide. So if I remove this, the system has to shift this way so I could make carbon monoxide. So I balance it out, I go back to normal. So it would shift to the right also. You guys are following me so far? Okay, I'm going to repeat this again because this is the first time you see this. So the Chatlier principle, you add a stress to the system, it would have to react to it. It will react to it, it would adjust to offset it. So if I add this, if I add more carbon dioxide, now I have too much of this, it would have to shift to the reactant to consume it. Okay? Now what happens if I take this one out? If I take this one out, it would shift this way, so it would make more of this to go back to balance it out, to go back and adjust the offset. So far so good? Okay. Now, what happens if you have more volume, okay? If you increase the volume. Now, let me ask you this. If you have a bigger house, can you put more people in it or less people in it? More people, okay? So this is how I like to teach this. If you increase the volume, then the equilibrium is going to shift to the side with a higher number of gas molecules, okay? So it will shift to the side with a higher number of gas molecules. So if you look over here, where's my red pen? I had a red pen. Oh, right here. Let's look over here. So I have 1, 2, I have 2 molecules or 2 moles of gas molecules. Over here, I only have 1 mole of the gas molecules, okay? Very good so far. Now, if I increase the volume, what's going to happen is going to shift to the side, is going to favor the side with a larger number of gas molecules, which would be the product side. So I increase the volume, is going to shift to the side that has more moles of the gas. So far so good. So this one would shift to the product. So it would shift to the product. Again, think about this. The bigger the place, you can put more people in it, right? So I increase the volume, is going to shift to the side with a larger number of gas molecules. I have 2 gas molecules here. I have 1 gas molecules there. Yeah? Okay. Now, I increase the pressure. One thing I told you at the beginning before I put this up, I said the pressure and the volume, the relationship is the opposite, right? So if I increase the volume, it's going to shift to the side that has a larger number of gas molecules. Now, the pressure would be the opposite of that. If you increase the pressure, it's going to shift to the side with the less number of molecules. So that would be, it would be shifting to the reactant. It would shift to the side that has less moles of gas molecules. We're good so far? Okay. Now, what happens if you increase the temperature? What happens if you increase the temperature? Well, increasing the temperature, that actually has to do with if you have exothermic reaction or if you have endothermic reaction. That's why I give you the delta H of this reaction. The delta H of this reaction is negative 201 kilojoules. What does that mean? That is an exothermic or an endothermic? That means that's an exothermic reaction. Okay? That's an exothermic reaction. Okay? Now, when you have an exothermic reaction, what does it mean to have an exothermic reaction? Exothermic reaction, you release energy. Do you agree? You release heat, you release energy to the surrounding. Endothermic reaction, which is delta H is positive, that means you require energy. You're going to get energy. So exothermic, you release energy to the surrounding. Endothermic, you get the energy from the surrounding. Okay? So this one is an exothermic reaction. When you have an exothermic reaction, because you're releasing energy to the surrounding, so technically the temperature is going to be on your product because you're releasing it to the surrounding. So you would put temperature on the product side for the exothermic reaction. Now, if I had an endothermic reaction, because I require energy, I would put the temperature on the reactant side, right? Okay. So far, so good. Remember, heat is a form of energy. So exothermic, temperature with the product side. Endothermic, the temperature would be on the reactant side. So now, we would just treat it like any other way. So if you increase the temperature, what happens if you increase the temperature? What do you think? Pause me for a second and think about this. So what do you think is going to happen if I increase the temperature? Here's the deal. If I increase the temperature, that means I have too much of this. It would have to shift to the left to consume this, right? To balance it out. So if I increase the temperature, because it's an exothermic reaction, the temperature is going to be on the product side. So if I increase it, it would have to shift to the left to balance it out because I have to consume this. Sounds good? So it would shift to reactant. It would shift to reactant. Okay. Now, what happens if I remove the water? What happens if I remove the water? Okay. Do you remember a couple lectures ago when we said we do not include liquid and solid in the equilibrium equation, right? We do not include liquid and solid in the equilibrium constant equation. So, what happens if we remove H2O? Nothing will happen, right? It's not part of the equation, right? Because we said liquid and solid technically they have a constant molarity, so nothing's gonna happen. So, what happens if we remove the water? Nothing is going to happen to it. So far, so good? Alright, last one. What happens if I add a catalyst? If I add a catalyst, what happens to this reaction? Which way is going to shift? To the right? To the left? What do you think? Catalyst speeds up the reaction. Kinetics has nothing to do with thermodynamics. So that could be a tricky question on the exam. That always used to get me when I was an undergrad. So kinetics has nothing to do with thermodynamics. Don't mix those two things. Kinetics is going to make the reaction go fast, but it has nothing to do with equilibrium. Yeah? Okay. Alright, so now that we've done a problem, it was so much easier to explain the Chatlier. You're doing a practice problem. I want to go over this one more time with you. So what does the Chatlier principle say? Now that you've seen some more. So if you add a stress to a system in equilibrium, it would have to shift, adjust itself to offset the stress. Like what we do, right? You have something happens, you challenge, you have a stress in your life, you have to adjust to offset that and go back to the normal, go back to the stable state. So in this case, I added CO2. If you add, now you have too much, you will have to shift to the reactant to consume that. If I remove carbon monoxide, now I don't have this, I will have to shift this to make some. Okay, now if you increase the volume, it's going to shift to the side that has higher number of moles of gas. You have 2, I have 1, so you shift it this way. Remember that, bigger the house, more people you can fit, right? So if you increase the volume, it's going to shift to the side that has more molecules, gas of molecules, moles of gas. Now pressure is the opposite of volume. Remember that, pressure goes up, volume goes down, so then it will shift to the other side if I increase the pressure. Temperature has to do, you have exothermic, endothermic. Exothermic temperature goes in the product side, endothermic temperature goes to the reactant side. Now you just treat the temperature as a reagent. So if I increase the temperature, that means I'm adding more to it. So now I have to shift to the reactant to consume that. So basically, treat temperature like any other reagent. All right. Now, removing water, don't forget, solid and liquid, they do not make a difference in equilibrium. They're not part of the equilibrium equation. So nothing will happen if I do anything to the liquid or solid. And catalyst, that's kinetics. You don't care about kinetics. We're talking about thermodynamics. Sounds good? Okay, we'll do more practice problems later. So this is the Le Chatlier principle. I will see you guys next time.